Okay, yeah, whenever you're ready, you can start.
Okay. So as Rick said, I'm a 2008 graduate in the same program you're in. So just 4 years ago, I was in your seat. I go to grad school. So what I'm going to do is I'm going to talk about what grad school is all about, talk about the different types of degrees, which you may have already seen before. So was everyone here when Roby Polikar came? Yes? Yeah. So Roby Polikar was my advisor for my master's degree. He's my co-advisor for my PhD. He is been on my candidacy committee, and I'll talk about that. And he's also on my doctoral dissertation committee. So it's been that a while. So a little bit about myself, and as I said, we'll talk about the PhD. I'll tell you what a day in the life of a grad student is like, and then I'll give you some tips if you're thinking about it, or just some suggestions that you should consider if grad school is in your future. So currently, I'm a PhD candidate. I don't call myself a student anymore. I'm a PhD candidate in the Department of Electrical and Computer Engineering. I started in July of 2011. Prior to that, and so I'm in the EC department. Prior to that, I did my ECE degree, the Master's of Science at Rowan University, so it took me about 2 years. And just as I said before, a few years before that, I was actually sitting in your seat wondering if grad school was going to be for me, and obviously it has because I'm going for the PhD. A little bit about my history of employment. I have been in academia most of my life, if it isn't clear. But I started out at Cortec. Is anyone here from Cortec? No one here from Cortec? No. So I started out as an intern for a year. I was hired full-time as an engineer, and they knew I was going to leave in a year. So a year later, I had left to go to Rowan University, and what's been paying my way was a research assistantship that I received. I'll talk a little bit more about that. I was hired as an adjunct professor, so I taught a course which would have been equivalent to the second half of Macy's analog systems, so solving electrical circuits with capacitors, inductors, and you're looking at solving circuits with differential equations, and Gauss transforms, and phasors and all that fun stuff, so everybody remembers that. Right now, I'm a research and teaching assistant at Drexel University, and that'll probably continue for another 2 years or so until I finish. So what we're going to start out doing here is I'm going to talk about the different types of degrees, what's going on with each one of them, and we'll get into a little more details, and then we'll start talking about specifics and what grad school is all about in terms of the research. So there's a Master's of Engineering, which is typically 30 to 45 credits to get. It's all coursework, and usually you see a project to finalize the degree. So that's what I'll finish in. There is a Master's in Science, which is, again, generally 30 to 45 credits. However, it's not all about classes anymore. So you'll take fewer classes, which sounds great as a student, and you just do more what would be equivalent to courses in terms of research credits. So you work on a project that's very focused, very specific, and at the end of it, you'll give a thesis defense. You'll have this big, long, 100-page paper that shows a culmination of all the work that you've done for about, an entire quarter on a specific problem that interests you. So a thesis is more rigorous than any project that you would ever see coming from a Master's in Engineering. And then there's the third type of degree, which is much different, which I've highlighted in green. It's different than either one of those two because it's not about coursework. It's not about taking classes, although you do have to take some. It's all about research. It's about 90 credits. It takes about 4 or 5 years, sometimes 7, up to 10 years to get. So it takes a very, very long time to earn a PhD. It's generally 90 credits. Nearly all of it's research. Most of the time, once you get past the Master's of Science with the PhD, you won't take classes anymore. You'll be done with it. And it all becomes about your research at that point in time. Thesis is most definitely going to be a requirement, as you're going to have to get up and give a dissertation. And it comes with 3 general milestones, and I'll talk about them a little bit later. You have your qualifiers, you have your proposal, and then you have your defense at the end. Your proposal is probably most intense one of those. So the Master's of Engineering, if you're not familiar with it, it's all coursework, as I said. but it's generally geared more towards somebody who is currently working and the company is paying their way to get through. So if you want to be a practicing engineer and you want to pick up a master's degree along the way and your company says, hey, we'll pay for it, this might not be a bad way to go about doing it. However, if you think the PhD is in your future, this is not the route you want to go because it lacks any research. It's all about taking courses, much like an undergraduate degree is. It's all about taking classes. That's what it is. Whereas the Master's of Science has research credits associated with it. Funding is generally going to be very difficult to obtain here because there's no research involved. Because there's three different types of institutions that you see. You see educational institutions, you see institutions that are about a 50-50 split with education and research, and then there's the very, very large institutions like the University of Pennsylvania and Drexel, which is primarily research, and then the education is a much, much smaller portion of it. Which if you're interested in doing a PhD, that's a very, very good thing. But the funding is difficult because when funding comes in, it's generally going towards PhD students who are going to be working on research grants. And engineering, and Master's of Engineering, if you're working on classes, you're not working on research. So essentially, you take the classes you want until you meet your requirements, and then you're done. So there's no research required. The Master's of Science is going to be a little bit more research-oriented. It's not going to be as intense as the PhD, but you'll take your courses, you may take, instead of 10 courses, you'll take 7 courses, depending on where you go. And then you take a little bit of research credits. And generally, the Master's of Science is picked up along the way until you get the PhD, so it's just something that happens. It usually happens around the time you take your qualifier exams. So the idea here is fewer classes, more research, but you get the, I guess, it's not a better degree, but it's, research and academia is in your future. It's a more advantageous degree to take. Many companies may actually rank the Master's of Engineering and the Master's of Science equivalently because they're both master's degree. However, that's generally not the case in academia. So as I said, if you're looking at doing your PhD, you want to have a Master's of Science. And the reason is because the PhD is a research degree. So you want to go in there showing that you can do research, you're successful at it, and if you're successful at research, generally you'll be a good PhD student and a good PhD candidate at that point. A thesis defense is generally required to graduate, so you spend all this time doing this research, you write this big long paper, you give a presentation for about 40 minutes, they tear you apart, and then you either graduate or you have to do it again, which usually you don't want to do it again. You only schedule that defense when you're absolutely certain you're going to get by. Funding is generally more readily available because now your education now has research associated with it. And I keep saying research over and over again. And I'll go over in a couple of slides what I actually mean by that because it's a little bit different than looking at how you deal with your undergraduate when you're taking courses. So I think the cool thing about the Master's of Science is that A, you have a master's degree, which is great. But you get to kind of get your feet wet with research and get your, you get to work on a problem that's generally open-ended and it doesn't have a solution. And I think that's pretty cool. You can find these problems, you can develop these problems that no one has an answer to. You can look in the back of your DSP book and look for really, really hard questions to solve. But the point is that somebody knows the answer to one of those problems. With research, that's not the case. You may have an idea about how to solve a problem, but it's not like you can go to any textbook in any library or any piece of literature that's out on the IEEE's Explorer's website and find a solution to the problem. So I think that's a pretty cool thing about this concept of working on a research-driven project as opposed to just taking classes. But it's a different type of problem that we're working on. So why would you consider going for a Master's of Science or a Master's of Engineering? I would say the big things are going to be better pay, better starting positions, more responsibility, and it's easier to advance. However, that is kind of conditional on you not being lazy. And the reason you would say why you're going to get better pay and better starting positions, if you have the Master's of Science, you've already shown that you can work independently on a problem, and you can develop a solution to that problem. And if they wanted to say, well, what'd you do? You have your master's thesis, you have your defense and everything that you prepared for it. that you can show them or to show a future employer. And generally, the Bachelor's of Science and the Master's degree will look better than someone applying for a job that just has a Bachelor's of Science. So it's really advantageous to get it. And they're a lot of work. There's a lot of work to get a graduate degree, but it will pay off in the long run, for sure. And another reason to go for it is if it's going to help you get ahead or achieve a goal. So if you want to work on a problem that I don't have a solution to, and no one else has a solution to, that's in a field that you're very interested in, that's a reason to kind of look at going after a Master's of Science, but you don't think that research is going to be in your way completely. Or perhaps maybe a position at a company requires a Master's of Science, getting one would allow you to take that position. Okay, so getting a master's degree, you're going to work longer hours, you're going to work a lot harder, but you're still going to have plenty of free time and to keep your mind active and do what you want to do. When you start to go towards the PhD route, you're starting to look at research as becoming a very, very large part of your life in terms of working on it a lot and just the amount of time that you spend doing free time is now spent researching other areas and continuing your research. So we've kind of discussed the Masters of Engineering, the Masters of Science, and kind of what goes into them. And I've been throwing this word research around a lot. So now it's kind of time to talk about the PhD and what actually goes into this idea of research. And the PhD, as I said, it's different than the Masters of Science and the Masters of Engineering. With one point, it's all about the research now. You'll take classes, and that's fine, but when it comes down at the end of the day, what it's going to take to get a PhD is research. It's about presenting your work, or doing your work, presenting your work, and having it accepted at conferences and journals. And that all culminates to the end to actually get your PhD. So the degree is definitely, it's not for everyone. Yeah, I think most people can go out there and get a master's of engineering or a master's of science, and they can move on and get a very, very good job. But the PhD really requires that you're very, very, very persistent. You can't stop because there's a lot of milestones. There's 3 big milestones that you have to pass in order to get it. So there's fewer classes that you can take. As I said, you only generally take what would be required of a Master's of Science. And then past that, it's all research credits from there. And there's 3 different milestones that we generally encounter with the PhD. There are the candidacy exams, some people call them qualifiers, the proposal, and the defense. So as I said, I'm a PhD candidate, and the way candidacy works is varies from institution to institution, but generally there's some type of test, whether it be a written test or an oral examination, where you go up in front of a committee, you research a topic, you present it to them. You have to have some original piece of material that builds on top of all those other topics. You go up in front of a committee, they tear you apart for an hour, and at the end of it, you either become a PhD candidate at that point, which pretty much says you're on track to graduate, or you have to take the qualifier again. And generally you have 2 shots. So at the end of the second shot, if you don't have if you've not passed candidacy, they'll generally ask that you leave the program and just finish with your Master's of Science. So that's a very big hurdle to get past. But one of the biggest ones, I would say, is the thesis proposal, which is what's going to be, this is what I want to do my dissertation on. So it's going to be critiqued very heavily by your committee to make sure that you have a very, very strong idea before you move on. And then if you get to the point where you're looking at doing a defense, generally your advisor won't let you schedule that defense without being extremely confident. And as I said, it takes 4 to 5 years to get this, maybe longer, maybe up to 7. Whereas the Masters of Science and Masters of Engineering, you can usually pull that off in a 1.5 years or 2 years. So the PhD is definitely a very large time commitment, and it is a different type of degree than the Masters of Science and the Masters of Engineering. Okay. And generally, funding is more readily available to PhD students. That's not to mention that it's not available to Masters of Science. I was funded through a research assistantship at Rome University. And at Drexel, I'm also funded through a research and teaching assistant, which essentially means I work in a lab, supposed to work in a lab about 20 hours a week, and I'm supposed to teach about 20 hours a week. And that pays my bills, it pays my tuition, and it gives me a stipend to live off of. There are those who are fortunate enough to have fellowships from places like the NSF, the DoD, and the Department of Energy, and some companies will actually fund a PhD as well. But the general consensus is that you're doing research, there's generally funding available to you. And I guess the final point here is that your job prospects are going to be much different with a PhD than it would be with a Master's of Science, or even or definitely in terms of somebody with a bachelor's degree. Because research is going to become a much more integrated part of your life and a much more integrated part of your career, which may actually make you overqualified for many positions that you could apply for. So my average day in a week, what it's like to be a grad student. So I get up at like 8 a.m.-ish, 8 to 9, you know how tired I am. Catch the subway to Drexel, and then I work for a few hours doing my research and other duties that I would have to work on. I take a small lunch, and I go right back to my research and other duties, at which point I'll decide whether I want to go to the gym, or if I'm especially busy, I'll do this research thing again. And then I'll take dinner very, very late. And then when I get home, I just don't stop working. You know, generally, I'll continue to read for myself. You know, maybe I'll pick up a book on game theory and decide that I want to teach myself game theory. This is the time when I'll grade papers, I'll grade labs, I'll grade quizzes, I'll grade exams, because I try to keep my research separate from my teaching responsibilities, because when I'm in lab, it's all about getting research done. When I go home, I'll deal with grading quizzes, developing solutions to exams. Not every instructor will give you a solution to a midterm exam or a final exam, so you have to do it, which means you kind of have to be confident about the area that you're teaching. Or I'll work on my homework that I have to do. You know, as a student, as I take classes, I still have to do homework. But what is this? What does the research really entail? So I came up with an abridged list of what I do at any given time. So much of it is spent reading papers. A lot of it is spent reading papers, like reading technical papers that have been published in the IEEE. And to be able to read these papers, you have to have an understanding of the research area that you're in. So not only the fundamentals of the field, say digital signal processing maybe, but if you're trying to read these advanced papers on digital signal processing, you need to know everything that's going on around them to be able to understand what's going on in the paper. So you'll spend a lot of time reading papers, reviewing papers for conferences and journals that might get accepted, writing code, verifying code, all about, you know, maybe developing new methods, and then, you know, doing all the data analysis associated with implementing the methods and testing them, and the statistical analysis associated with them. And then once you have this method developed, you've analyzed the data, you start writing conference papers and journal papers, and if they get accepted, you have to get the material ready to go to the conference. And this is all research-based. You have to deal with the lab meetings. You have to have meetings with your advisors. Usually I meet with my advisor 2 to 3 days a week to show them results. So that's generally, you have to be doing work every day in lab. Or else that meeting is going to be like, well, what'd you get done yesterday? You don't ever want to be like, well, I don't know what to do. You want to be on top of your game. Another part is dealing with students. So as a teaching assistant, I have to hold office hours, I have to grade, and I have to deal with students' questions regarding their grades and why they got what they got, and a whole bunch of other stuff. And then on top of that, I have to go to class as well. So I guess the point to take away here is there's a lot of different things involved in research, but a lot of it is just expanding your education on what you know about a particular area that you're focusing on. So if you're focusing on digital signal processing, you're reading and reviewing papers in that specific area. You're writing code to solve problems in that specific area. You're preparing and analyzing data from the methods that you've developed. So it could be a number of different things, but it could be also a lot of other things I didn't mention on here. So here's a few tips that I actually pulled out of, so Mark Drenz and Hannah Wallach have, I think, a really, really good paper on what it takes to be a successful grad student in CS, and in particular natural language processing. But I think across the board, these bullet points go across engineering, any other field that you'd be looking at. So particularly for the PhD, research is always going to be number one. And with the Masters of Science, it's going to be heavier, but research is always number one. So it's not about classes at this point. You want to talk to other students. You want to know what they're working on. And you know, how does your level of work compare to their level of work, or how does their workload compare to your workload? And it's good to get an idea about what other students are researching as well, because it may help you with your own research along the way. Everyone works differently, and I think one of the things I was told when I came to grad school is that research doesn't necessarily start at 8 o'clock in the morning. A lot of people think of having like an 8 to 5 job. There's people that may come in at 2 o'clock in the afternoon, but they'll stay later because they work better evenings than they do in the morning. So it's important in terms of getting research done, what time works best for you to actually be most productive, which kind of keeps into play of keeping a regular schedule, as I have one for myself. Prioritize, you guys already get this from your senior project, and making action items. This is one of the more important ones, I think, about grad school, is when you make action items, you want to, you have something that you want to do, and you want to continue to make these as you go along throughout your degree. Generally, something is wrong if you're waiting for your advisor to tell you what you do. You always want to be the one who's in control of your research, and you don't want your advisor to be the one who's holding your hand and pulling you along, because at the end of the day, when you graduate, you should know more about the area than your advisor actually does, which I think is definitely true in every case that I've seen. You want to keep a log of everything you do. I use Evernote. Getting things done, that's self-explanatory. And if you're working day in and day out, it's important once in a while to keep a social life going, because as I said, if you're doing that schedule every single day, it becomes tiring and it's easy to burn out, so it's important to get out once in a while. And in research, it's okay to get stuck once in a while because you're working on problems that it's not clear to see the end of it. So it's easy to get stuck in maybe some mathematical set of details that you're just not able to get by, and you just need a boost from somebody else to get you by. So it's okay to get stuck, but it's even more important that you learn from your mistakes if you do get stuck along the way. So I have, I think, 5 sets of suggestions if you're thinking about grad school. So I tried to put these together and kind of keep them kind of condensed, but if you have any questions, let me know. So I think the biggest one is hands down mathematics. You have to be good, and you have to have a diverse set of math skills. When I was here, I took Calc 1, Calc 2, Calc 3, ordinary differential equations, linear algebra, probability statistics, and I think that's all I took here. But
I have a quick question here.
Yeah.
When you took linear algebra here, how difficult a course would you say it was compared to other linear algebra courses?
I didn't think it was too difficult. Linear algebra can be difficult depending on how it's taught.
Yes.
I think the most difficult part that I had about linear algebra, and I will say this, even in like the large schools like Drexel and engineering, you'll talk about, does anybody know what the eigenvalue problem is? I think a lot of people know what it is. Like they know, like if I asked somebody to write down the characteristic equation, they could do it. But if I asked you, well, really, what does it mean to have an eigenvector? What do the eigenvalues actually mean? It's like they get fumbled. And that's, I think, topics you don't see towards like graduate level courses. But I don't think it's that hard.
Maybe a better question would be the linear algebra course was sufficient for you.
Yeah.
Okay.
Yeah, I mean, you get everything you need.
Yeah.
So, and what I mean by linear algebra is basic linear algebra to be able to go on to grad school. So you want to know about inner products, matrix inversion, the eigenvalue problem, determinants. What does determinant mean? What do the eigenvalues mean? What does an eigenvector mean? All this stuff is very important. And it's one of those things that when you take higher level control systems, image processing, signal processing, machine learning theory, you have to have a background in linear algebra to be able to get by. So, and I think all these courses are offered here, and I think you pick most of them up along the way, right, to get the degree. So, so math is cannot be understated enough of how much it is needed in graduate school. Second would be programming. Being a good and efficient programmer is a skill that not everybody has. And I think it pays off for you if you are a good and efficient programmer. And it's not just being able to program in one language, but having a general idea of how to program in any language. So understanding object-oriented programming is really important. Understanding what a class is, understanding what an abstract class is, understanding what an interface is, and what these mean in terms of a software project is all very important. And learning to write scripts, I think, is a very powerful thing, whether the scripts be in MATLAB or some program like Python. Learning at least one scripting language is a good thing. MATLAB is generally used in academia very, very heavily, more so than C, C++, Java, Python, Perl, but all of those other languages are very important. So knowing at least 2 or 3 of those may help you get ahead, depending on what you're working on. So another thing to maybe look at is research on your own. And it's something to look at in baby steps. You don't start out by trying to prove some massive theorem about something. You start out by doing something small. So if your senior project would call for like an automated decision to be made about something, like maybe a pass-fail, maybe you want to look at some machine learning algorithm, some detection and estimation algorithm, using like the Pearson lemma to determine whether you reject or fail a test. So math, programming, and a little bit of research to get you started with grad school. And the last set is intentions. So at the end of the day, you really have to be motivated about what it is that you want to do. Okay? So just because you're book smart doesn't mean you're necessarily going to be successful in research, but the opposite isn't true. You want to be in a research field and you want an advisor that has similar goals to yours. So if you're going to grad school, and the only funding available is for nanotechnology and you're interested in signal processing, it's probably not going to be a good fit for you in that lab. You want your advisor and yourself to have similar research goals so that you can both benefit. And if you are going to go to grad school, you should research your future advisor actually pretty early. So research them, go to their website, read some of their papers. It may be a little tough to read at first, but it's not a bad idea to do. And then try to meet them in person if you can. I think a face-to-face meeting with your advisor is much, much better than any type of email transition that you can send it to them. And I think one of the biggest things I see as I grade papers is writing abilities. Usually in undergrad, they're not the best writers in the world. I shouldn't use horrible, but they're not the greatest writers in the world. So I think writing and learning to write well is a skill that is very beneficial, because when you start to write conference papers and journal papers, you have to have very well written English, so your English skills have to be very good, and you have to be able to communicate to the audience that you know what you're talking about and very clear.
Do you think reading those papers will kind of get you used to the way
Yes.
those things need
Yeah,
to be
and
written? They're entirely different than
they're
other
written
things.
entirely differently, because so I'll give you an example. When I write a paper, I assume that there is some level of knowledge that is already that the reader already has. So I wrote a paper on it's called Fusion Methods for I don't know. But essentially what we were doing is we were trying to identify speakers in a database, and the problem is that the speech signals that we got were collected from a phone system. And essentially what happened is they used different sessions to record people's just plain written or spoken text. And what would happen is halfway through this study, they changed the phone system used. So, and I know he's laughing back there, but the problem is that if you have this detection algorithm out there and you're feeding these, we were using autocorrelation coefficients, or something derived, Kepstrom, which is way outside, we're going to talk about it. We were using these Kepstrom coefficients to predict the speaker, but the problem is that if you change the recording equipment, you've changed everything about the channel. So there's like new channel distortion being added, the features that might describe an individual have now changed. So you have this like abrupt change, and we were trying to figure out, well, how do you get robust features to predict on somebody, even if there is a change, and how do you combine multiple experts together to boost the accuracy of the system. Yeah, but I mean, essentially what happens is what I was getting at the end is that it's written in a way that I expect there to be some level of knowledge understood by somebody before I can write the paper. So I don't talk about how the Mel Ketchum is implemented. You know, I just jump right into Mel Ketchum and what's happening with it, what we're improving upon it. Yeah, I mean, technical papers are written in a very specific manner. Okay, and if you read 2 or 3 of them, you can generally get the idea of how they're written. So that's all I really had going on. If you have any questions, you can feel free to email me. You can visit my website and get an idea about what I'm working on at any given time. If you can't remember the website, you can just Google me. I should come up right away.
You come up right away.
I do?
Yep.
Okay.
Google's first.
Google's first, okay. If you're interested in this how to be a successful grad student, just look around, Google for Mark Dred's. Him and Hannah Wallach have a really nice paper on what it takes to be a successful grad student. And if you're interested, I'd really recommend reading it. It's very good. Okay. Does anyone have any questions?
What are you going to do after you get your PhD, you think?
I think I'm going for tenure track faculty positions. And as I said before, that's when the work starts. The PhD is just something my goal is to be a tenured professor at a university, and the PhD is something I'm getting along the way to get there. So
You've heard that. After he gets his PhD, the work starts.
Yeah.
It should be some fun to it too. I mean, it's
I
pretty
mean, it's
cool.
a lot of fun. I mean, if I wasn't enjoying myself, I wouldn't be able to deal with the 10-hour days every single day. So it's nonstop, but I love what I'm doing, so I have no reason to not do it.
You always were a pretty hard worker, but when you went on to graduate school, did you have to step up to get, some you work, like about 15 hours a day now?
Because when I first started, I'd say my linear algebra skills were basic.
Right.
I don't think I was fantastic. I didn't even understand what the implication of the eigenvalue problem was. I didn't have a strong background in probability theory, and I was going into machine learning. If you know anything about machine learning, probability theory and linear algebra are pretty heavy. So I spent a lot of time, so to be able to read those texts, you had to go back and reference books on probability, books on linear algebra, just to be able to get through the main text of what it is that I'm trying to learn. And then once I have the machine learning down, now it's time to move on and actually read some research papers. So it's nonstop. If you're reading a paper and you're reading something about somebody's method and they say, oh, well, we use Blackwell's approachability theorem. Does anyone in here know what Blackwell's approachability theorem is? No. So you have to go and Google it and look it up. And then you can get back to reading the paper and trying to understand what's going on. Yeah.
Where could I go to get a hold of good papers from respected colleges like MIT or Carnegie Mellon on physics or robotics?
It depends on what you want to do. So the IEEE is an amazing resource, but you have to have the subscription, and that's usually expensive. So what I would recommend,
What I'm talking about is
research. So there's been this push in the journal community to go more public access, and there's one major place I would tell you to look, and it's the archives, ARXIV, if you can remember that. It's based out of Cornell. You got it? And they have books, these very, very technical papers on physics, mathematics, various areas inside of mathematics, computer science. So I find myself in here reading